second part involves the 1G to 5G cellular mobile phones significant features, and the third part involves the detailed presentation of the channel modeling of the 5G communication system. So let me start with the first presentation. Screen can check again. Not nothing. Okay. Okay. Leave. Okay. The contents of my presentation are like this. First 1 or 2 minutes, let me accustom with this system. There may be some problem with this audio and video problems. First 1 or 2 slides are 1 or 2 minutes only. So the contents are like this: wireless communication system from a signal processing perspective. The second part of this first presentation involves the impulse response, system response, and frequency response. And the third one is the signal processing and communications perspective of the multipath propagation and time dispersion. Time dispersion and this Doppler effect and frequency dispersion effect. So these are my contents to be discussed in the first session. Wireless communication systems. So usually this acronym WCS stands for the wireless communication systems. They are analyzed usually in time domain. We use convolution. For this purpose. A similar analysis can be done in frequency domain. For this purpose, we use a tool known as the frequency Fourier transform. So these are the two tools we use for analyzing the signals. Using Fourier transform, the main features you can see here. Every input signal can be represented as a group of cosine waves. A sine wave or cosine wave, usually we specify it with a particular amplitude and phase shift. So likewise, the output of the system, DFT can be used to represent every output of the signal, in similar form. So in the first slide, what we were discussing is for analysis of the signals, we use time domain. For time domain, we analyze the signals in time domain and frequency domain. We use two tools. One is the convolution tool, other one is the Fourier transform tool. Fourier transform, we use it to represent the input side, and DFT, it can be represented the output signal in the similar fashion. So that means any linear system can be completely described by how a particular system changes the amplitude and phase of cosine waves when the signal is passing through that system. So this information is called a system's frequency response. I repeat, by using frequency Fourier transform or convolution in time domain convolution tools, we can describe any linear system. However, how that particular system changes the input signal when it is passing through that system, how its amplitude and phase of that particular signal are changing. So this particular information is called the system's frequency response. Since both the impulse response and frequency response contain complete information about the system, so there must be one-to-one correspondence between the two. I repeat again, impulse response means the relationship between impulse response and the frequency response is one of the foundations of the signal processing. A system's frequency response is the Fourier transform its impulse response. You can see here, there are two parameters I am using here. One is the frequency response, other one is the impulse response. Frequency response is the response of the system when a particular input is given, whereas the channel response is the impulse response. So now let me compare the system operation in time domain and frequency domain. In time domain, you can see here, if the input signal is convolved with the impulse response, same in the previous slide, whatever that information integral I have represented in the convolution operation. So y of n is my output information and x of n is my input, h of n is the channel impulse response. So you may ask a question, so what is an impulse response function? As the name suggests, so this function defines the how something responds to some input signal. So which we call it as an impulse. Usually the impulse function that we use in all our signal processing techniques are delta function. Usually we normalize this impulse and it has a value 1 at t equals to 0, or we call it as a unit impulse. Impulse response means, I repeat again, response means the signal, impulse response is a signal that exists a system when a delta function is input. I repeat again, impulse response is the signal that exists a system when a delta function is the input. So there are two parameters here, impulse response and frequency response. Impulse response is the response of the channel when the input is delta t, impulse function. System response or frequency response is nothing but the response of the system for the given input. It computes, system response is computed using the input as well as from the impulse response. So you can see here, in time domain, I can represent discrete signal x of n. H of n is the impulse response, y of n is my frequency response or output response in time domain. So similarly, the same thing can be converted into frequency domain. I can represent with x, capital X of f, h of f, y of f. So I can convert this x of n into x of f like this in both ways. Similarly, h of n can be converted into h of f, capital H of f in both ways. Similarly, output also can be converted like this. So if you see in frequency domain, the same operation can be represented like this. Here the inputs are the spectrum. Input spectrum, when it is multiplied by a frequency spectrum, frequency response is resulting in the output spectrum. So usually we use DFT and IDFT to relate the signal in the two domains. So you can see, suppose for example, you see here a signal is represented in time domain here, this part, and this is represented in frequency domain. So this is the time domain signal. In time domain, you can see here some sample numbers and corresponding amplitudes are given here, but you cannot make out so much of information from this impulse response of that particular signal using time domain. Whereas in case of frequency domain, you can see here the x-axis represents the frequency, y-axis represents the amplitude. We can get beautiful information from the frequency. You can see here, in between the frequencies, starting from 0.19 to 0.32, something like that. So the channel is, this system is giving response, and the amplitudes of these frequencies are almost 1.2 to 1.3 amplitudes, whereas the rest of the time, the rest of the frequency components are zeros. So you can get more information from the frequency domain than the time domain information. So you can see here, coming to the impulse function. You can see here, as I said, impulse function, usually we define the impulse function with this one. As I have mentioned, it is represented and this is 0 when t is greater than 0. Okay, so the same thing is given here. So this is the impulse response, delta function out in time domain, and you can see here its frequency domain also I can write here. Its frequency domain can be written here. This is the impulse response of the frequency domain. So it's a flat curve, horizontal line only. So it contains. So now in the coming slides, let me discuss with the how and why how this impulse function is used to estimate the channel output. Similarly, why do we go for impulse delta function as to describe the impulse response function only? Okay, I repeat again, we are using the impulse response and input signal to obtain the output signal. Okay, so to get the impulse response, I use the delta function, which is defined like this. So you may ask a question, why we should go for only delta function? What are its significant features? Let me discuss. You can see here only one thing. This is the time domain, and it's in frequency domain. You can see here its response is like this. It's a flat curve because it contains all the frequencies. Impulse delta function contains all the frequencies. Let me discuss it. Let me show it by using a MATLAB program here. So before going to the giving the example, so let me one more time discuss about the impulse signal significant features. So this impulse signal is composed of sinusoids of all possible frequencies. So that is why I'm getting the frequency response curve as a flat response here, and the amplitudes of all sinusoids are the same, and the phase shift also all the frequency components are also 0. And all signals are made up of sinusoids, and usually the signal to be analyzed is made up of different amplitudes and phases. So since an impulse contains sinusoids of all possible frequencies, if we know a sinusoid, if we know a system response to an impulse, then we can easily predict how it will respond to any input. I repeat again, the impulse function, that is delta t contains all the frequencies, all the possible frequencies with same amplitude and 0 phase shift. And the signal to be analyzed will contain different sinusoids of different amplitudes and phases. So the link is, if we know the system's response for an impulse which contains all the frequencies, then we can easily predict how it will respond to any given input. This is the logic that we follow while estimating the channel response in any wireless communication system. Only 2 points only here, because the impulse signal contains all the possible sinusoids, and signal to be analyzed contains different amplitudes and various phases. So if we know the response of the system for a given impulse, then we can easily predict the response for any new input. Okay, so let me show here. This is the signal, a small program to create a sinusoid signal with various varying frequencies. You can see here cos of 2 pi ft here. Suppose if I substitute f equals to, let me say 5 here, f equals to 5. This is the, when f is equals to 1, I get one sinusoid. F equals to 2, I get two sinusoids. F equals to 3, I get three sinusoids. And what I do, and f equals to 4, I get four sinusoids, and f equals to 5, I get five sinusoids. I have not given the fifth sinusoid figure. Let me discuss something about this program here. What this program does is, it creates different frequencies, sinusoids, and it adds all those sinusoids, and we can see what is the response of it. Okay, my idea is how to create an impulse function. I said an impulse function contains all sinusoids of the same amplitudes and zero phase shift. Okay, a particular spike impulse function is nothing but when t equals to 0, a particular spike, how it contains all the sinusoids. So what I'm doing, I am starting from various sinusoids and coming back to the impulse function. So this program generates various sinusoids of our choice and adds all those sinusoids. So I create first 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, like this. And I'm adding all those 5 frequencies. You can see the response of it. So when I add all the 5 frequencies, 1 heads plus 2 heads, 3 heads, 4 heads, 5 heads, I'll get this kind of response. Okay. Similarly, let me create more and more frequencies. You can see here. If I choose this f as suppose 10 here, then I can get already 5 I created, 6, 7, 8, 9, 10 here. 10, and if I add all the 10 frequencies, 1 heads plus 2 heads plus 3 heads, so what should I get? You can see here. So this is the summation of all the sinusoids starting from 1 heads to 10 heads. So what is your observation is here? There will be only one, something like an antenna radiation pattern. You will get one main lobe followed by the side lobes like this, or harmonics. Okay. Amplitude of the only one main or peak level is high, and rest of the amplitudes of the side lobes are very at their minimum values. Okay. So how did I obtain this figure? I have created different sinusoids with the same amplitudes at the zero phase shift, and I summed up all the sinusoids. Then I got this figure. And if I create 100 sinusoids, I will get, and I sum up all the sinusoids starting from 1 heads to 100 heads. I get the sum of all the signals like this. You can see here there is a spike here at time t equals to 0. You can observe here x-axis is the time and y-axis is the amplitude. You can see here at time t equals to 0. At time t equals to 0, you get at time t equals to 0. You can get this is at time t equals to 0. Time t equals to 0. This is the time t is greater than 0. This is t is less than 0. This is t is greater than 0. See, there is a spike. So how did I obtain? I have summed up some 100 sinusoids. 100 sinusoids. Then I get an impulse function like this. Suppose if I create 1000 sinusoids, what do I get? You can see here. Suppose if this is 1000 sinusoids, let me create by just simply varying this f value to 1000. Okay. See here, I get a clear spike here. This is the impulse function. Okay. This is nothing but my delta function, which is equivalent to 0 for t equals to 0. You can see here, this is my t. This x-axis is nothing but the t. And this when t equals to 0, I get a spike which is called an impulse. It's called an impulse function. So this is how I created a impulse function. How did I create? I have generated different sinusoids and I summed up all the sinusoids. One sinusoid, 1 to 1000 sinusoid this is. You can see here 100 sinusoids, 100 sinusoid signals. Like this is 1000 sinusoids. So I got very clear. If I add more and more sinusoids, I mean, I will get a straight, I will get a spear like this, a spike like this, only clear spike like this. Okay, this is how I get a impulse function. Sorry, this is 1, delta equals to 1, and when t equals to 0. So this is how I get. This is how I created delta t, and why do I use this delta function to get the impulse responses? So it contains all the frequencies of equal amplitude and zeros. I write again here, impulse function contains all the frequencies, contains all frequencies, and with equal amplitudes, and zero phase shift, Okay, so this is why I use the impulse function. So this is one case. This is first case. Okay, this is the characteristic of the impulse function. And the second point is the signal to be analyzed contains all the. It may contain signal to be analyzed. May contain all possible frequencies. Varying phases. So these are the two characteristics here. So with the first one, since it contains all the frequencies with equal amplitude and phase shift, zero phase shift, the signal to be amplified can be analyzed, or I can predict system's response if I know the impulse response of a particular system for any possible new input. Okay, so let me go again. So this is what I drawn conclusions here. You can see here. So if I pass an impulse through a system, so that is effectively the same is passing all sinusoids through that system. This is what I assume, because this impulse function contains all the sinusoids with the equal amplitude and zero phase shift. So the same thing I have written. If I pass a signal, you can see here. If I pass an impulse like this, okay, so it means it is effectively passing all sinusoids through this system. Okay, then the response you can see here. Okay. This is my the frequency response will be like this. If I pass a impulse function, this impulse function del of t through a system, so what I get here? I get the frequency response of a flat frequency response. Okay, this is my frequency response. And amplitude. Okay. So this is what I said. So passing an impulse function through a system, through a channel means effectively impulse means the passing all the sinusoids through this system. Okay. So this is the frequency response. This is what is written here. This impulse signal and its frequency response is given here. Okay. It's a flat response. Okay. So once if I know the impulse function response of the channel h of t or h of f, once I know for any possible new input, so let it be as x of t in time domain or x of f in frequency domain. Since I know impulse response in time domain, impulse response in frequency domain, so that I can easily obtain for any new possible input. Okay, through convolution or through multiplication here, I get my y of t or y of f here. Okay, so that is what is shown here. Suppose if I pass a signal, a new signal like this, so their characteristics are like this. The first signal characteristic is maybe some less than some 0.5, second signal characteristic is 0.8. If I pass it, if I make it to pass through this system, how it responds to, you can see here, signal. So, and if we know the system responds to all those sensors, what is the case of, which is the case of the impulse response value. So now coming to the, so far what I discussed is, so far what I have discussed, let me denote it here. How for channel estimation, for estimating the, for estimating the received signal, this is my channel, this is my receiver input, and this is my transmitter output. Okay. So now what I'm doing is I am modeling my channel as in with impulse response h of t. In frequency domain it is h of f. So for any given, and using this I compute the receiver input at maybe r of t or r of f for any given new input. New input. So if I know the h of t or h of f of the channel, I can easily obtain my output, which is the input to the receiver for any given new input. Okay. Okay, let me now from here onwards, few more slides are there. So what I do from signal processing and communication perspective, how the wireless communication system can be analyzed. You can see here. So any wireless communication system, what for the purpose of using any wireless communication is to transmit information via or using an electromagnetic wave or radio wave, or sound waves or acoustic waves, which has become everywhere. It has become everywhere. Means wireless communication has become everywhere in the world. And in many of these situations, many of these systems, the transmitter and the receiver are both are mobile. This is the kind of scenario. To transmit information, we use electromagnetic waves in case of radio communication, sound waves in case of acoustic communication, and the wireless communication is everywhere. And many of these situations, both are mobile, or maybe one of the transmitting or receiving source may be mobile. So even if both link ends are static, even both the transmitter and receiver both are not moving also, there will be some scatterers. And what are those scatterers? You can see here, what are those scatterers? The scatterers means, generally we use the term here, scatterers. Means the objects that reflect here, that scatter, that diffract, the propagating wave. When a wave is impinging on a particular object, it may get reflected back, or it may scatter, or it may diffract. Okay, so which may move with significant velocities. Their velocity also gets changed. Once a wave is getting reflected, its velocity is getting changed. Similarly, scatterers change. But for all these three terms, I use the single term known as the scatterers. So here, what I'm saying, generally we use a transmitter for sending the information, a receiver for picking up the information, so which will be sent through a channel. Here, both may be moving, or one of them may be moving. Transmitter and receiver, both may be moving, one of them may be moving, or both are static. Both are static. Static means both are not moving. they are stationary. Even then, there will be scatterers. Okay, so because of the scatterers, you can see the situation of how the propagating signal is getting affected. What propagating signal is getting affected. So these situations means this because of this scattering of the signal propagation, this kind of signal situations give rise to the time variations of the wireless channel. So this is the effect of the scatterers. This is the effect of the scatterers. So it varies the propagating time of the wireless channel. Okay, and it is mainly due to the Doppler effect. Okay, and this kind of wireless communication channel is called linear time variant channel, LTV channel. Okay, linear time varying channel. This is what is known as the linear time varying channel. Okay, so I repeat again. Uh, this is the scenario. You will have to transmit information from a source. You will have a transmitter to pick up the information. You will have a receiver. So in between the media is the channel, and the scenario is both may be moving. Transmitter and receiver both may be moving, or any one only moving, or both are not moving. Even in all the three cases, signal gets affected because of the objects which are there in the channel. And this particular phenomena is known as the scatterers, because of the objects means which are the scatterers. And scatterers means the effect may be due to the reflection, scattering, or diffraction. So because of these scatterers, what is happening is there will be a varying in the time of the wireless channel. Maybe it is mainly due to Doppler effect and time delay spread. Both are there, and we call the channel which causes the time delay spread and Doppler effect at the receiver. The channel which causes the delay spread and Doppler effect at the receiver is called LTI. Okay, we call this LTV. Sorry, LTV, linear time varying channel. Okay, the channel which causes the propagating signal as when it receives at the receiver, when it causes a delay spread and Doppler effect, it is called LTV, linear time effect, linear time varying channel. Okay, so this linear time varying channel effects are known as the time frequency dispersive effect and time frequency selective effect. Okay, let me discuss how these effects are, how these two parameters or phenomena is affecting the signal quality. How the arrival time of the signal at the receiver is affecting the signal quality. Similarly, how the frequency is getting changed. Okay, and whether it is flat response or selective response. Let us see here. Okay. So now we have started to transmit information from a transmitter to the receiver. It has to propagate through a channel, and we consider the channel as a linear time varying channel because this channel causes variation in the propagation paths, which causes a delay spread, which causes a delay spread and Doppler effect also because of the scatterers in between the transmitter and receiver elements. Okay, this is the point. And this phenomena can be described using two phenomena. What is known as the time frequency dispersive effect and time frequency selective effect. One is the flat response effect, other one is the selective response, frequency selective effect. So next slide. You can see here. In wireless communication information, this is power. Okay. Okay. And the same thing I have discussed in the previous slide itself. So in all wireless communications, information is transmitted by modulating the radio wave at a particular carrying frequency, and by means of it, and it is broadcasted and it is emitted from the transmitting antenna, and it is getting picked up by the receiving antenna. This is what a communication system says does. So behavior of the electromagnetic waves usually we can determine by propagation environment according to Maxwell's equations. Okay. And for most scenarios of interest, solving Maxwell's equations is infeasible. It is impossible, you can say. What I can say, we can predict the behavior of the propagating signals. I repeat again. The above sentence says that to send the information, we use the transmitter antenna and we use the receiving antenna to pick up the energy. Okay, so in between is the channel. Okay, but the behavior of this wave, electromagnetic wave, can be determined. Usually, we determine pre-space communication. We can determine the behavior of the wave using Maxwell's equations. To some extent, only free space loss only can be if there are no multiple paths. But the problem in most of the cases, like urban environment and mobile cellular communication purpose, solving of Maxwell's equations is highly impossible. It will not give us the solution because of the multipath propagation. Multipath propagation. Okay, I repeat again. The behavior of the electromagnetic waves which are transmitted at the transmitting antenna and picked up by the receiving antenna at the receiver side their characteristics can be modeled using Maxwell's equations in case if it is only a free space wave propagation or communication, where there will be only line of sight propagation involved. There are no multiple paths or propagation. And this Maxwell's equation solution is not the solution for mobile cellular communication as well as for the urban environment, particularly densely populated urban environment. Okay, it is mainly because of the multipath propagation. Okay, it is mainly due to the multipath propagation. Okay, because the problem is the electromagnetic signal is interacting with the. You can see here. If this is my transmitting signal, there may be a building here. There may be another object here. There may be another object here. So this is my receiving antenna. There may be a line of sight propagation like this. So the same thing goes here and comes here. The same thing hits some object and it comes here. Maybe through scattering purpose or through scattering process or diffraction process. The same thing again gets scattered, comes here. Okay, so different objects. So this, because that means the electromagnetic signal, this electromagnetic wave, EM wave, it interacts with several objects when it is in its journey. You can say when the wave is emitted from the transmitting antenna, it interacts with many objects in the media, and then only it reaches the receiver. Okay, it interacts with several objects. Okay, this is transmitter, receiver. Before it reaches the receiver, okay, electromagnetic signal, it interacts with several objects. It interacts with several objects and then only reaches the receiver. Okay, so except for free space communication, that is from satellite propagation, the electromagnetic wave interacts with many objects. These objects may be dielectric objects or conducting objects or semi-conducting objects. Okay, the same thing, let me discuss it in the next slide. So this is the fact is that except for free space propagation, the wave interacts with the dielectric and conducting objects. Okay, so the interactions are usually classified. We can classify them as reflection, scattering, transmission, and diffraction. So these are the four fundamental phenomena that occurs when the signal is propagating from transmitter to receiver. Okay, these are the four fundamental phenomena that occurs. Okay, so when it is transmitting from a transmitter to receiver, okay, when it is reaching the signal may get affected by the reflection, scattering, transmission, and diffraction. Okay, so the behavior of radio waves strongly depends on the carrier frequency. Again, this characteristics changes with respect to the carrier frequency, also thereby the wavelength of the signal. You can see how the wavelength of the signal affects the quality of the amplitude and phase of the signal when it is picked up by the receiver at the receiving end. Okay, for the case of flat fading and frequency selective fading, we can easily describe that both fadings using the wavelength parameter. Okay, and you can see here the presence of multiple scatters. Scatters means there may be buildings, trees, buildings, hills, which cause RF to propagate along several different paths. Okay, this is the trees. There may be building, vehicles, hills. They may be moving or not stationary. Okay, these are the principal scatters. Scatters, what I mean here, it's causes scatters means I'm combining all the parameters: reflection, diffraction, scattering. Okay, there are four parameters you can see here. You can see, we have seen here, there are four things. And transmitted signal after reflections, a part of it may be transmitted, a part of it may be reflected. So these are the things. So hence, a receiver picks up a superposition of all multiple objects. You can see here, when by the time the signal comes at the receiver block diagrams, okay, it may be due to a direct line of sight communication, may be reflected from some object, may be diffracted and gets reaches at the receiver. Okay, so it is nothing but the signal summation of all the signals. Okay, x of n, where n equals to starting from 0 to n minus 1, and I can say it's a del of n minus t, del of n minus tau. Okay, the summation of all the input signal components. So this particular phenomena is referred to as multipath propagation. Okay, so let me see here. Multipath propagation, how the delay spread and Doppler effect affect the signal propagation with some numerical example. With that, we finish this first session. So due to different lengths of propagation paths, individual multipath components experience different delays, which is called time shifts. Okay, due to different propagation lengths. Okay, so individual multipath components experience different delays. Delays are nothing but the time shifts. Suppose this is the signal. Okay, this is the signal. So by the time it reaches the transmitted, by the time it reaches the first signal, a copy of the first signal may reach by the time the second transmit pulse is received at the receiver. See here. That means there will be an overlap. The third one, the second will reach at the third one again. So there will be an overlapping of the signals here. Okay, the first component will reach if there is a line of sight component as it is, and if there is a reflector, it reaches the receiver by the time the second pulse receives the receiver. So there will be an interference here. Similarly with the third symbol also. Okay, so this the receiver observes the temporally spread, time spread version of the transmit signal. This is what is called time spread. Time spread. Okay, so that means the net effect of the time spread is this is the if this is the symbol to be transmitted at the transmitter, let us say its time, tau, its time is t tau, its time period is tau. So by the time it reaches the receiver, the time spread, the delay spread, because of the time spread, its time period gets larger. See, tau plus td. This is the effect at the receiver. This is the transmitter. Okay. So the net effect of the time spread is the signal time period gets spread. Signal time period gets spread. This is the time spread. Time at the transmitter. By the time it receives the receiver, it gets spread. Time is spread actually. This is t plus tau. This is t. You can say here. This is t. This is t plus tau. Because of the delay spread, you can say. So even though the medium itself is not physically dispersive, in the sense that the different frequencies propagate with different velocities. So such channels are termed with time dispersive. So in the next slide, you can see here, as a practical example I give for both the things. One for the time spread, other for the Doppler effect. Okay. Practical example is, consider two propagation paths in a static environment. Okay. Suppose if this is the transmitter, okay, receiver. Consider two propagation paths. It is receiving, this is one with the tau 1, and there is some reflector here. It receives here with tau 2. So the received signal in complex baseband domain. Okay, I am not multiplying it with e power minus j omega t. Only the original symbols are taken here. So it will be, as I said, in any channel communication, if I know the channel impulse response, I can calculate my output R of t for any given input like this. Okay. In frequency, in time domain, it is R of t equals to convolution of S of t with H of t. Okay. Or I can with t minus tau, actually this is t minus tau. I can put this tau here, either here or here. There is no problem. T minus tau. The delay. So, okay. Usually we write here S of t minus tau with H of t. Okay. So the same thing in, because I have received one signal with delay tau 1, another signal with time of arrival is tau 2. The same thing is here. So received signal is nothing but the summation of both the signals. The input signal with its delayed version is convolved with the impulse response added to the second path delayed by, which is delayed by the tau 2, convolved with the channel response H2. Okay. Here H2, there can be n number of multiple paths. Okay. So P is the pth path, or you can write this HP as nothing but it's a complex attenuation factor here. It's a complex attenuation factor. It can be represented with modulus of H of P times e power minus phi p. Phi p is the subscript here. Okay. And the tau p is the delay associated with the pth path. Okay. I can write it for the n number of signals. Same thing, same expression. Okay. So this is the complex attenuation factor, which involves the amplitude change term, okay, plus phase changing term. Okay. So this is the amplitude changing term, and this is the phase changing term. So the net effect is the signal which is received at the receiver is changing its amplitude as well as its phase because of the several effects, maybe the time delay spread or Doppler effect mainly. Okay. So let me discuss the a small example, time delay spread. So the same thing I have written here. If I consider two paths, Once a signal with delay tau 1 and signal with tau 2 is the impulse responses. This is the summation of both the two. Okay. The magnitude of the Fourier transform I can represent like this. If I represent it in Fourier transform here, okay, I can represent like this of the received signals as follows: that is R of t times e power minus j pi e power minus j times 2 pi ft dt. Okay, if we convert it into Fourier transform, this is the equation. This is the general form of the received signal, and received signal for this signal. All right, let me show it here. This is the general Fourier transformation equation for any given R of t signal. This is the Fourier transform. So for this one, this is the Fourier. This is the received signal. Received one. The Fourier transform of this received version is like this. Okay, it's so complicated. You can see here. You can observe that. So what we did is, this is the channel whose impulse response is h of t. I got my R of t here. Okay, I have sent my S of t. There are two S signals. Okay, and by the time, because of this channel, R of t is nothing but it's a summation of two signals here. Okay, so for this purpose, I have converted, this is a time domain TD. I have converted to the frequency domain for two signals, for two paths. You can see the term here is the delay term here. There is a phase change. Okay, and there is a attenuation factor, and here you can see here it's a multiplicative effect. Channel impulse response is multiplicative here, H1 times H2. You can see here. Okay, H1 times H2. Okay, it's a multiplicative. So it can be seen that time dispersive channel has a multiplicative effect. It's a very dangerous thing on the transmit signal in the frequency domain. So if I take the frequency domain, if I analyze the signal which is received at the receiver for two paths, okay, if I transform into frequency domain using the Fourier transform, you can observe that there is a multiplicative effect on the transmit signal. Okay, so this multiplicative effect is very, very significant. So therefore, a time dispersive channels are frequency selective. This multiplicative effect means it's a frequency selective. We'll discuss it. What is this frequency selective? It's because of the multiplicative effect of this H1 and H2. In the sense that different frequencies are attenuated differently. Okay. So this is how actually frequency selective is coming into a picture in case of wireless communication channel. Okay. So next, coming to this, you can see this effect, this multiplicative effect graphically. Here you can see here. So differences in attenuation here. This is the differences in attenuation. So one is the H1 is the attenuation of the signal which arrived at the receiver with the tau1 delay. H2 is the attenuation of the signal which arrived at the receiver after delay of tau2. Okay, if the differences of the attenuations become more severe when the difference of the path delays is large and the difference between the paths attenuation is small. There are three cases here. I consider what will happen. Okay, you can see here. First, let us see if the difference between the attenuation means this H1, as I said, in the frequency domain term of the receiver, we have seen that in the frequency domain term, channel, this is receiver, transmitter, because of two multipath components here, two paths with delays tau1 and tau 2. Okay, there we have seen that a big equation here with tau 1 delays and with R of f, the frequency domain in form of the received signal. Here we have seen, okay, that with H1 term, H2 term, and multiplication of H1 and H2 term, and delay term tau 1 minus tau 2 term, phi 1 minus phi 2 term, and the delay spread is multiplied with the frequency again. Everything we have seen in that previous equation. Okay. So let me analyze the difference between the H1 and H2. Okay, the attenuation, the H1 is the attenuation of the signal 1, H2 is the attenuation of the signal 2. If the difference in attenuation become more severe, that is one case. Small, let me take the small one here. Okay, if the difference in attenuation is very small, means tau 1 minus tau 2, and this is the case first. Difference in the attenuation become more severe if the difference in the delays is very small, and if the attenuation of the H1 is much larger than the H2. So this is the signal case. You can see here this one. Okay. Sorry, this one. This one. So that means if the difference in the difference in the time delays is very small and the attenuation difference is very high. Okay, difference in attenuation is very severe and the delay path is very low. Then you can see here the frequency response of the signal at this point. Okay, frequency response is not much significant. So all the these are the amplitude term. Is the amplitude term. This one. That means almost all the signal components are getting passed through the channel. Only some frequency components are attenuated here. This is the frequency, na? This is the frequency. Few component signals are attenuated like this. Okay, this is the original amplitude like this. But some frequency components are getting attenuated in a varying nature. It is the case of the delay is very difference in the delay is very small. Difference in the attenuation is very high. Okay. In second case, you see if the difference in time delays is very high, and the attenuation is also attenuation difference is very high, then it's the case you can see. You can see how the signal amplitude is changing. You can see here. This is the frequency. So different frequencies are getting affected differently here. You see here. In third case, you see the time delay spread is arrival time delay difference is small and almost similar. Attenuations are almost equal. Then this is the case. This is the dangerous case. See here. This is the frequency amplitude. See how some deep fades are there here. You can see some frequencies are getting affected severely, and some frequencies are not getting affected. Their amplitudes remain the same, but some are getting severely. So the last case is the dangerous thing. If the time difference or time arrivals of the two paths is very big, and the difference in the attenuation is very small. This is the very dangerous case. So this, if you see the frequency response in this kind of propagation paths, two paths I have taken. We see here there are deep paths here, deep fading paths. This is the frequency. This is the amplitude. Okay, how the amplitude of the signal is affected for different frequencies. Okay, there is a deep path. That means you don't get any signal level here. Okay, the amplitude is supposed to be here, but you can see many deep paths. So multipath propagation is not the only source of the time dispersion. And usually we think that multipath propagation is the only source of the time dispersion, but there are other sources of time dispersion. So they are the imperfections in the transmitting and receiver sources. Oscillating frequencies may be different. Pulses are not satisfying the Nyquist criteria. That may be the one reason. And in fact, imperfect time recovery or sampling at the transmitter as well as at the receiver side. These are also other few causes which affect the propagation path. Okay, so this slide you can see here, if the difference, the varying differences, the differences of the attenuations which are received at the receiver, because of the two propagation paths, the variation is maybe bigger, approximately and equal, then what will happen you can see here. It is severe effect is there. Okay. So this is how a practical example we had taken here, how the time spread affects the signal propagation quality at the receiver. I have considered two propagation paths. Now you can see here. Uh, Now we can see Doppler effect. Now let us take the second example, which is Doppler effect. Okay. Earlier we had taken the time dispersed effect. Now you can take the Doppler effect. Okay. Doppler effect. As I said, I have been mentioning multipath propagation affects the received signal quality in two ways. One is the time spread. So other one is the Doppler effect. Time spread we have seen with numerical example, how the received signal is getting affected, how the received signals amplitude is changing. Phase we have not considered, only amplitude. And now let us see Doppler effect now. So in many wireless systems, the transmitter, receiver, and scatterers are moving. Okay. So this is the transmitter, receiver, both may be moving, or the object maybe it may be a scooter or truck, something like that. It also may be moving. Okay. This is the stationary object. Okay. So all the three components may be moving. We have a transmitter and receiver in media. Media may be static or may be dynamic. Okay. So in such situations, the emitted wave is subject to the Doppler effect, and hence experiences frequency shifts, means variation in the received frequency. Okay. So when only receiver, let us consider only the receiver is moving with a velocity v. Let us consider this case. So then we can say a pure sinusoidal carrier wave frequency with Fc, which is observed by receiver RC here. Okay. Only with the receiver is moving. Other transmitter and scatterers, maybe objects within this, may not be moving. Then you can see the Doppler frequency waveform here. This one. The phase phi is the Fc is the carrier frequency, transmitted carrier frequency, and phi is the phase angle of the signal when it is arriving at the receiver relative to the direction of the motion of the receiver. See here we consider that receiver is moving. Okay, is the angle of arrival of the signal relative to the direction of the motion of the receiver. Okay, and the C naught is the speed of the light. See, you can see usually we see that we will assume that V is less than C naught. The movement of the signal, receiver or transmitter or scatterer, may be much less than the velocity of light. Then I can approximate this one to this one actually. This is the Doppler frequency, or I can say observed frequency. Observed frequency of the signal, frequency of signal at receiver. At receiver. RX stands for receiver, at receiver. Okay, so it depends on the carrier frequency, transmitting frequency, velocity of light. This is a constant, there is no problem, but it may vary with the transmitting carrier frequency and velocity of the receiver velocity, and this is the phase of angle of arrival of the phase, which depends upon the scatterer. Okay, means in objects which are in between the transmitter and receiver. So the received frequency at the receiver depends upon the movement of the object, movement of the transmitter or receiver, Here I have considered only receiver. If transmitter also movements, you need to consider the transmitter movement velocity also, frequency. These are the parameters. Now, how it affects the signal quality at the receiver, you can see here. So consider for a transmitting signal ST with the Fourier transform of SF, expression of the received signal, same thing can be expressed in the receiver. Fourier transform in Fourier domain like this actually. Okay, R of F is equal to H of H times S of alpha F. Okay, where alpha is this factor actually. I have substituted alpha with these terms. Okay, so H is the complex attenuation factor, which includes complex means it includes the phase as well as the it includes the phase as well as amplitude terms. Sorry, amplitude and phase terms complex. Okay, so complex means e power minus j phi term, amplitude phase term. Okay, so this is the frequency domain version of the received signal frequency term. Okay, for this one. Okay, frequency domain, time domain, this is frequency domain. So now let me take again two paths. Receiver is receiving the signals in two paths and how the signal is getting affected due to the Doppler effect. You can see here. Consider two paths. Two propagation paths with equal delay. Here I'm considering the equal delay because which gives the most significant effect. And but Doppler frequency velocities are different, V1 and V2. See, I am considering Doppler effect at the receiver. Okay, this is the antenna. When it is two signals are received at the antenna with the same delay but different velocities. Okay, this is my transmitter. Earlier we have seen the time delay spread. Now we are seeing the Doppler frequency spread. Okay, maybe it may be scattered from a particular object. There may not be any line of sight propagation here. Okay, this is the situation. We have seen that R of T we have seen, received signal formula we have seen, and its frequency domain formula we have seen. Okay, so now what I'm saying, the frequency domain equation of the signal which is getting affected by the Doppler frequencies, you can see here R of F. Here this is the frequency domain equation. Okay. And again, this H term involves the complex attenuation factor, the amplitude term and phase term. The magnitude of the received signal, you can see here, this is the term, this is the magnitude term. Okay. Earlier version you have seen, this is the magnitude. So this equation 1 represents the frequency dispersion, and the equation 2, this is the equation 1, you can say here. Okay. Sorry. And the equation 2 describes the Doppler effect leading to time varying multiplication modifications of the transmit signal in the time domain. Okay, multiplication, you can see multiplication effect, and this one, let's see, time varying multiplicative modifications. You can see time varying multiplicative, these velocity changes modifications. You can see here. This is how a signal received at the receiver changes its characteristics because of the Doppler effect. It's a frequency multiplicative effect. Okay, then you can see what will happen with this Doppler effect. We'll see. I will discuss it in the second session slide. Okay, because of the Doppler effect, what will happen? Frequency deep fades how occurs and how to overcome those deep fading in case of mobile communication channels. Okay, so with this, I think last slide. This is in the first session. There is an advantage of this multipath propagation. So many times this multipath propagation is a disadvantage in all the cases. But there is some advantages if you try to utilize this multipath propagation characteristic into your advantage. Okay. So about the multipath propagation has traditionally been viewed as a transmission impairment. It's not unwanted thing. But nowadays there is a tendency to consider it as beneficial, since it provides additional degree of freedom that are known as the delay diversity or frequency diversity. So this can be exploited to realize diversity gains in the context of MIMO system. Okay, this is not our topic. What I'm saying, the problem that is associated with the multipath propagation communication can be taken it as an advantage also by incorporating this particular characteristic in a particular configuration as the MIMO. MIMO, what I do, I try to utilize the same characteristic, multipath propagation characteristic, in the name of delay diversity and frequency diversity advantage. Okay, that I am not discussing here. This is the last slide, and here with this, the first slide, first session is over. What we have discussed is so what are the causes for multipath propagation? Okay, this is what we have discussed. And the second one is how multipath affects how multipath propagation affects the signal quality, quality in the sense amplitude and phase at receiver. Okay, and we have taken this effect in terms of two things: times delay spread, timer delay spread, and we have explained it in two examples. Okay, by taking two paths, one path with tau 1 delay, other path with tau delay. We are taking the time domain signal, converted to frequency domain, and we observed that there is a multiplicative effect in the frequency domain of the two terms. Okay, which is leading to the frequency selective fading that we have seen. Okay, similarly, Doppler effect also we have seen when the things are moving. Okay, how severe it is also we have seen. Okay, in addition to this, initially we discussed. Okay, any channel can be characterized. Characterization of the channel. Okay, channel is characterized using impulse response, that is delta T. Okay, I call it as impulse response. Why I have taken this delta T function as it contains all the frequencies with equal amplitude and zero phase shifts. Okay, and the signal to be analyzed may contain all the possible sinusoids, varying amplitudes and phases. So once I model the channel using the impulse function, which contains all the frequencies, then I can easily predict any incoming new input. So that is how I can create a impulse function. I have seen by adding many sinusoids with equal amplitude and zero phase shift. But also, this is what we have seen it in. Anybody wants to ask any question? Anybody is having any question, please?
Dear participants, anybody having any doubt or any clarification?
Okay, take a 2 minutes break and we will continue the second session. Is it okay, or shall we take more time break?
Okay, sir. 10 minutes enough.
Okay.
Okay, sir.
How much time, madam?
10 minutes, sir. That means 11:30 or 11:35 we will start the session, sir.
11:30 will start. Okay, fine.
Okay, 11:30. Okay.
Thank you.
Dear participants, so at 11:30 the second session will start. So as you know, this is an ATAL FDP. So ATAL FDP directly generating the certificate. Okay, so ATAL FDP won't be generating the certificate until unless you are maintaining 80% attendance, and also at the last we are conducting the text, and in that test also you have to get above 60%, at least minimum 60%. Okay, so that's why for all the sessions you should listen, and we will provide the material from our resource persons. Okay, assignments will be given, and the feedback will also be taken for every day. Okay, and that feedback form only consider as a attendance. So you have to maintain at least 80% attendance. Okay, so the next session will be starting at 11:30. The same link, one more thing, the same link is for all the 5 days. Okay, whatever Zoom link we are provided for this inaugural and for the first session, that will be same for all the 5 day sessions. Okay. Any more clarification, you may free to ask. Any doubt or any clarification required, you may ask.
Okay, madam.
It's okay. Oh. So let us take 5 minutes break, and we will rejoin again at 11:30. Thank you.
Okay, ma'am.
I repeat again, the delay spread, the main component, the main effect due to the multipath effect can be classified into two parts. One is the delay spread, other one is the Doppler effect. Delay spread main effect is we have seen it spreads the symbol period of the received signal. Okay, and we have seen that the effect of the multipath propagation due to the delay spread mainly varies in different ways because of the two, mainly it varies with the two factors: difference in the attenuations, one factor, and other one is the difference in the time delays. How I have classified them into four types: difference in the variations of the attenuation, difference in the variation of the time delay, and we have seen most effective way, most significant, the worst situation of the multipath effect. We have seen it when the attenuation is zero. It means difference in the attenuations are zero, and the time delay is more. That we have seen. Similarly, when the Doppler effect also we have seen how the deep fades can occur because of the Doppler effect. Doppler effect means it is mainly because of the movement of the transmitter, receiver, or reflecting objects. All the three components may be moving, or any one of the component may be moving, but sometimes you may see that Doppler effect may be more severe than the time delay spread. I have not compared it, but you can practically you can observe it. I have some results if you want. We can show. But I'm with this. I'm stopping the discussion of the multipath propagation. Third session is there. If we have time, the more details on the multipath effect with the results. Okay, with the detailed description. But for the time being, second session, If we have time, we'll go for the third session. This is the second session. Since till now we have discussed about the radio channel effects on the wireless communication signal only. So let us discuss about the various generations of the wireless communication. What is a wireless communication system? Why do we go for, in this session, what we discuss is why do we go for a mobile communication systems? Evolution of mobile communication systems. What are the differences between the various mobile communication systems? What are the main components that are involved in the wireless mobile communications? This aspect only we'll see up to OFDM. Very brief details about the OFDM, and then followed by the third session, if time permits, or at least few minutes, we'll discuss about the third session. In this session, I have only few slides only, maybe around, I think 20 slides only. Repeat. Let me start this second session, starting from the 1G to 5G wireless communication generations. Before discussing these are the contents of my one minute. So the contents of my presentation in the second session are like this. Let me begin with basic principles of communication systems. Basic principles of communication systems. Under this item, let us say what are the resources to support a mobile communication system, and what is the generic architecture of a mobile communication system, and various design aspects of similar communication systems. Okay, what are the difficulties involved in while designing a particular communication system? Let me repeat it again. Let me remind you, I am just touching the very minute details about all these topics. Okay, I'm not going into the depth. And what the rapid development of wireless communication system, what are the causes for this? Or I can say significant features of the wireless communication system. Only one slide only here. There are the 6 slides. This is one slide. And what are the limitations of the current cellular system, that is from 1G to 4G? What are the limitations? This is one slide again. And this is the prime thing. Evolution of cellular systems from 1G to 5G. More we can say about the 5G features. Why do we go for a 5G system? Okay, maybe 2 to 3 slides, 2 or 3 slides, maybe 3 slides, I believe. Okay, and what are the various complexities involved? We have seen the radio channel propagation, but here it is different thing. What are the various complexities involved in the 4G communication systems so far? Okay, with the signal propagation because of the multipath propagation. This is different thing. Only 1 or 2 slides on here. Okay, and then very basic details of waveform system. Only 1 or 2 slides here. Okay, maybe I think this is 1 or 2 slides. 1 slide. Okay, so these are my contents. I begin with basic principle of communication systems. Here I cover the frequency reuse. It is known to you, but only 1 or 2 slides. Okay, and the resources available, that is MAC systems. Okay, generic architecture of the communication system. Okay, so this is the basic principle of communication system, slide number 1. So usually you can see the picture here. Communication from mobile station. This I call it as a mobile station or mobile phone. In general, we call this as a we call it as a mobile station or MS, and this we call it as a base station or BS. Okay, this is the we denote mobile station with this acronym. Okay, so communication from mobile station to base station, this is the communication. Okay, it takes place on uplink. This is what is known as uplink. Okay, and the